Good evening, Shivramakrishna sir.
Good evening, sir.
Yeah, good evening, sir. I think all the 40 members are participants are joined, sir. And within a short period, within 5 minutes, remaining people also joined, sir. Okay. Shall we start the session, sir?
Please, sir.
Yeah, yeah. Thank you, sir. Thank you. And also, welcome to all participants. Today, we are having a day 4, the second session. The session is on demonstration of 1 minute demonstration of FDM, fixed deposition modeling, and SLA, DLP, 3D scanner from Center for Product Design Development in Additive Manufacturing. It's a research center, Usmania University. Sir is giving live from the center only right now. So thank you very much, sir.
Okay.
Sir, you can go ahead.
Shall I proceed, sir? Sir, shall I proceed? Am
Yes,
I
sir.
audible?
Yeah, yeah. You can go ahead, sir.
Yeah,
Thank you, sir.
Thank you. So I welcome all the participants for the demo session on SLA, DLP, FDM, and as well as 3D scanner. So we have, I already told you in my lecture, we have a center called Center for Product Design Development Additive Manufacturing. So I am now presently sitting in the same center. Of course, I will be showing a video recorded demo of all the things with all the product, how you can make a product, everything. But definitely at the end, I will show the center also at the end of this program. The entire, what are the facilities we have here. To save time, I'm going to now start with the presentation.
Yes, sir. Your screen is visible, sir.
Are you able to see the screen, sir?
Yes, sir. Yes. It's clear.
Hello?
Yeah, it's clear, sir. Yeah.
Are you able to see my screen, sir?
Yes, sir. We are seeing your screen, sir. Yes.
Okay, right. Okay, right. So welcome once again to the demo session on SLA, DLP, FDM, and 3D scanner. So what you are seeing on the screen is the right side. You are able to see a SLA DLP system from 3D systems, and which can be used for using resin. You can make a product out of which. The popular products you can make a jewelry models, biomedical models, etc. You can make. And then the other one is the left side. You are seeing the Ultimaker S5 Pro dual extruding nozzle is an FDM fused deposition modeling machine with the 2 extruders we have here, one for the support material, another one is for the main part, or sometimes you can use as a single extruder also. Same material can be used for making the support structure and another part. And below you can see the, what you can call it as the scanner, you can call this the scanner you are having. So now let me start with first the theory behind this. That is I'm going to start with SLA DLP, then FDM, then Arctic Space Spider 3D scanner. So this is a Fab Pro 1000 SLA DLP machine. I hope the SLA DLP is different from SLA technology. Both came from 3D systems only, but SLA works on the principle of bottom up approach. That is, you have a part on a plate and the laser beam will move in the XY direction and the build platform will move down and you get a part built in the from bottom to top here like this. But here the laser beam will be projecting from top. But whereas in the case of SLA DLP, the projection is not a laser beam, it's a UV light. And from here you project a light here. And this build platform will be dipped in a resin tank, a resin plate in this, right? So here what happens is, as the laser beam, it will be at the bottom, and then the projection lamp, the UV light will project on it. And as the first layer is built, this build platform will move up like this. So here the part is built from bottom to, it will be coming from here, anti-gravity, from bottom the plate will come. Whereas previously, the part is built above the plate. Now the part is built below the plate. That's the difference here. So you are not using laser. So definitely the accuracy will not be as good as SLA, but definitely it is, when compared with the cast, it is having good precision. So this is ideal for engineering and jewelry applications, small part prototyping and direct 3D production across a wide range of high quality material. You have high quality precision parts up to 3 times faster, higher throughput print speed than competing systems. You have industry grade material for jewelry and prototyping. FabPro 1000 3D printer includes 2 print platforms, 1 print tray, Ethernet cable, and all. You have a, you will be also given a curing vessel you will be given here. So where you, after you build the part, you have to take it and put in a UV light curing cabin in which the part will be dried up, and then you can directly take it and use. So basically, stereolithography developed by 3D system. The co-founder officer Chuck Hull is there, right? So stereolithography is a form of 3D print technology uses for creating models, prototypes, patterns, production parts, etc. It uses the principle of photopolymerization. What is photopolymerization? Is initially the resin is in the form of monomer. It's a photosensitive resin. When you expose to high intensity light, that each monomer links to other monomer through a linking what you call photoinitiator, and forms a chain-like structure that will be a very hardened layer you'll get. Right. So once first layer is built, then again another new resin is spread on it. Again, the second layer cross section, the laser will move, and that second layer gets hardened up. So like this, the part gets built up in SLA technology. So the difference between the SLA and the SLA DLP, the new technology that came from 3D system, where you use, instead of laser, you use a UV projection lamp, and the lamp will projecting the light from the bottom, whereas the previously laser will come from the top. That's the main thing. So this is called direct light projection system. So it is it consumes less electricity and also less resin. So it is also very economical in use. That is the diagrammatic difference you can see here. Here the laser beam will be coming from the top, whereas here the DLP, SLA will be coming from the bottom. That's the difference. This is a photo, as I said, the working principle of chain-like structure, etc. You can see. There's a specification of this printer. 43 by 43 by 61.2 centimeter is a build envelope. Weight is 37.5 kg. Software we use is 3D Print. And this is the printing build size. You can go up to 125 by 70 by 120 mm. Whereas the above in the printer size. This the build size is 125 by 70. Maximum size of the part you can produce is 125 by 70 by 120 mm. Pixel pitch is 65 microns. And layer thickness is 30 to 100 microns, and wavelength is 405 nanometers. In materials that you can use is dual cast GRN, tough black, flexible black, elastic black, and photo gray. Application master patterns for vacuum casting tools, molds, dies, etc. Let us now watch this video to understand how the process is done in SLA-DLP. Now let us see the SLA-DLP technology here. So this is basically works on the liquid-based resin technology here. If you compare the earlier one, you see this FDM printer. You are sending a solid wire there, which you are getting heated through a heated nozzle. Build a part. Here it is not. This is a different way. Here the input material is in the form of resin. So for example, you will be using a resin like FabPro photo resin here. So this works on SLA. In SLA process, photopolymerization takes place. That means when a photo sends to resin gets exposed to high intensity light in the form of a laser or a UV light, that gets hardened up, and because of which that monomer starts coming forming the that is polymer. It becomes a polymer and become hardened. So in this case, for this process, what we have in our center is we have FabPro 1000 SLA DLP technology. Sir, are you able to hear, sir? Where you are going to build a part. Hello? The machine
Yes, sir.
specifications are
Yes, sir. Yes, sir.
able to 70 mm by 120 mm, and source
Yes,
is
sir. Your
it is a
audio is clear
ultraviolet
only.
light it is,
Thank you.
so it's not laser. For example, conventional SL stereolithograph apparatus, you use a carbon dioxide laser beam here, but in this case you will be using a projection light here, and then you are having different materials you can use, like dual cast green resin, or tough black, or flexible black, or biocompatible resins. So if you see what are the main components of these 3D systems, so this is this FAPRO 1000 is developed by 3D System, which is the original first inventor of Chakal for the 3D SLA technology. So same company produced this new one, SLA DLP technology. You can see this in this is the where the part gets built up here. This is the tank where you store the resin here, right? And the light will be coming from the bottom. This UV light coming, projector lamp will be there, will be coming from the bottom. And you can see at the here you are going to have where the actual part gets built up. This is the build platform where the part gets built up here, and you build in the reverse direction. So here it is not like the conventional anti-gravity, it is like, so the part gets built up from from top to bottom, it will come gets built up. That you will be seeing in the next video how you do everything. And because of that light, this layer will get hardened up, and here also the projection lamp will be moving in the XY direction, whereas this platform will be moving in the Z direction it is. And other interesting feature of this technology is the surface finish is very good. You can see some of the components produced using this technology. So this is a replica of the mandible. You can see such a fine tooth you can get here, but using an FDM technology, this much of surface finish you cannot get. But these components can be used for functional as well as for what you call concept modeling, etc. Also you can use this technology. So before you build this part in a FAPRO 1000, you will be first taking the resin and you will be mixing in the mixer, LC 3D mixer. So this is the first thing you have to take care, because if the resin is not mixed properly, then the part you build up will not be accurate. So first you will be mixing that resin on using this LC 3D mixer. This one, once you build this one, once you mix properly, then you will be pouring into this reservoir and building the part here. So once the parts get built up, in the post processing, you will be putting in this curing. That is where you will be curing the entire part, because it has to be, it will in the form of resin, it will some liquid type will be there, so that you have to dry it. So for that you put a curing, and you can see a lot of UV light coming here and curing it. So one of the drawback of this technology is sometimes the curing time will be more than your actual building time. And before you do this, initially you require a software. Whatever the STL file you develop is, you have to again do all the pre-processing in the software. That is, we have a 3D sprint software in which you give the required input parameters and then you start building the part. So that entire details of the entire process, how you do the build the part, input the parameters in the 3D sprint software, and how you load everything, that will be explained by Mr. Suranjan, and will be the technician in our lab on the detail of this process.
Hello everyone, my name is Suranjan, and today I am going to explain you about the DLP machine. So this machine, the name of the machine is FAPRO 1000, and the manufacturer is 3D Systems, and I am going to explain you about the complete process from the beginning, like how we prepare the resin. The material will be in the form of resin, which is a photoreactive polymer liquids. So when it comes in contact with light or UV light or some kind of projector, it gets cured. Like that, the build is there. So that we will discuss later on. So I will start from the pre-processing of the resin and how to prepare the file for print, and how to print here, and how to operate the machine from this control panel. And once the print is done, what to do with the part, and about the curing, and I'll explain all those things step by step. So let's start with the basic specification of this machine. So the build size, that means the build volume of the bit, that is 120 mm by 70 mm by 120 in X, Y and Z direction respectively. So we can build, the build volume is comparatively small, but it is very useful for prototyping medical devices and for very accurate components like which are having very fine surface finish. If you want, then you can go for DLP technology. So various materials that we are using here is dual cast green, tough black, flexible black, and biocompatible results also we use. The basic use of this technology in various fields like jewelry industry, we prefer this, and in dental, medical, and for prototyping of any kind of component, any small that should fit in our build volume. Based on that, we can use this printer. So the layer resolution that we can achieve is 30 microns to 100 microns. That is very fine and accurate. So there are basic protocols for this print. Like once we are done with the print, it has to be completely cured. That means we have to expose the part with UV light so that it can be cured completely. So when it is not cured, you won't get that mechanical property of that part. So the basic things, we will cover everything in this process. So let's start with the components of this machine and how the technology works. We will see that first. So let's see the components, basic components of the machine, and what are the things we have to add on before starting the print, or which are removable components, or which are fixed components, what are the thing, how it works, that we'll see now. So by pressing this, you can open the door. So once you open the door, we can see several items. Before that, I'll show you the removable items, what we can remove and we can place. So this is the vat on which we have to pour the resin. So this, you can see, this is a transparent film. So we have to pour the resin as per our requirement, based on, see, suppose the amount of resin we have to pour, it depends on the part size. So based on that, we will fill the resin in this. You have an indicator up to which level you have to fill. So based on that, we will fill the resin on this, and we will place this vat on this like this. There is a front side, we have to make sure that which is the front. This is the front side. So we have to place it like this. Once we place, we have to lock it. Since there is no resin, we are safe, but once the resin is involved, we have to be very careful. We have to wear the mask and gloves and other PPE equipments. We have to wear those things. So right now there is no resin. I have just fixed the bed. So what happens, how it works is, our bed, this is the build platform on which the part is going to build. Generally, we have seen part building like this, in Z-axis in positive direction, but this is quite opposite to that. Here, the build will be like this, upside down. Suppose you want to print this component, it will be like this, but when the print is completed, you can see the part like this. So it will build upside down. So this is quite opposite to the SLA technology. It is the parent technology is SLA only, stereolithography, but it works in a different manner. So they have named it to DLP, digital light processing. So the bed has to be fixed here on the top like this, upside down. So now this is the setup. So the projector will be here somewhere. So the projector, what it does, it will project the 2D cross section of the model that you want to print. It will have 2D cross section throughout the height. So the first 2D cross section, it will project here. So you have seen the vat is transparent. So the transparent film is there. The projector light will project the 2D cross section to that film, and the film is in contact with the resin, what we are going to pour while printing. So suppose the resin is here. So the 2D cross section will try to cure that much amount of area with the projector light. So, and meanwhile this bed will be below here somewhere. So when it cured one layer, that already cured one layer will be in contact with this bed. So like this, the bed will go up and down like this, and each layer will be get cured, and this bed will move up finally. And when the print completed, you will get the part like this upside down. So we will do that. So before that, I'm just giving this brief. When we will load the part, we will slice it. When we load here, by that time we will see it practically. So these are the basic parts in this machine. So before printing, the resin will be like this in a bottle. So what we have to do, we have to mix it properly. So we have a mixer there. So we have to mix this resin for at least 500 cycles. Once it is mixed properly, then only we can use this. And once the print is done, suppose this is the output and this is the file what we got. So it is because it is completely cured, that's why it looks very stiff and hard. But initially it won't be like this. When the print is completed, it will be very soft, and there will be support structures. We have to remove those support structures and we have to place this in the curing box that I will show you in the process. So this is all about the basic things. Now let's move to the slicing section. There I will show you how to do slice. So basically for slicing the file, STL file, the company has provided one software, that is 3D Sprint. So here you can see the icon. I'm clicking here. This is the software 3D Sprint. In this software we are going to slice the file and we will prepare the file for printing. So it will take some time to open. Yes. So this is the software interface, in which already it's written here Fab Pro 1000, that is the name of our printer which we are having. But basically 3D system, what they have done, they have given only one software for all kind of machines and whatever the technology they have. So here you have to select your required printer. Suppose you are having some other printer, then you can go for other printer. So we have selected here Fab Pro 1000. So we are moving to next. Here you have to select the material on which you are going to build the part. So right now we will select this proto gray. In this material we want to print our part, so I'm selecting this one. Next, gray is the shade. Okay, this is the, we are going to print in 50 microns. That is the finest resolution what we can get from this machine. We can get up to 30 microns, but 50 micron also it will give you very nice surface finish. So we select that 50 micron here, standard, set. So the printer has been set now. So you can see the data here, whatever data you have given, which material is loaded and what is the layer resolution for this. Everything is you can see here in X, Y and Z direction. The available build box you can see 123, 60.76 and 120 mm in G height. So now we will import the part which we want to print. So to import we can go here to the file, and here you have one option called import. By clicking here you will get to see this. Select this part. I want to print this one. This is one dental component. It is a prototype of something, some dental requirement. So we are going to print this part. So we have to see there is a red lining on the outer side of this part. That means this part is outside the build box. So first of all we have to bring this part inside the build box. For that there is an option called auto place. So when you click here, the part will automatically come to the center. Let's say set, it will come to the center. Okay, so this is within the build volume right now, and you can see here there is a gap between the part and the build plate. That is intentionally given, that is by default, because it has to generate some support structure here, so that when you remove the part should not be damaged. Only the damaged thing will be the support structure. So once the support is gone, you can clean the bed, you can clean the part. So for that purpose this gap is given. You can increase this gap, like you can move this part in X direction, in G direction, so if you want the distance to be increased. But this is fine for me right now. So if you want to scale this down, then there is some option where you can do that also. So now the part is at the center of our build plate. So there are several options here that we can check here one by one. So this is scaling by unit. So now the unit is in mm. If you want to convert it into inches, then you can go for here scale by units. Then you can see there is an option orientation. So in orientation we have three optimized things. If you want your print time to be optimized, then you have to click over here, and when you set orient, it will orient the part in such a way that you will get the minimum time in printing. You want a good surface quality, then you have to click here and set orient, so that it will orient based on your surface quality. And if you want support area should be minimized, then click here and set orient. So in this orientation, support structure will be optimized. So like this, three optimized categories are there. It depends on your requirement, on what based on your requirement you have to set it, and you will get the print. So the time will also vary. Suppose you are selecting the support area, the print time will be increased. If you are going for print time, the surface quality will be decreased. Like this, you have to compromise in something. So this is about the orientation. So we want to optimize the print time. So I'm selecting this print time, and let's say orient. So it's orienting like this. In this orientation, the print time will be very less. So now let's say to move to auto place. Let's say yes. There is something wrong in this, so we can go 2 step back, control Z here. Okay, so we are okay with this. Now there is an option called copy. Before copy, I will tell you about the transformation feature. In this transformation feature, you can move the part, you can rotate the part in any orientation. When you click on support, it will show you some option. So you have to select the kind of support what you want to give. Here it's flat, but there are tilted is also there. So we'll go with the flat only. So now here gate type of support is there. Once we click generate the support, then I can explain these things to you. So let's generate this. Yes. So these are the support. These are flat we have given, and see here you can manually also generate some supports if you want. If you feel like this area needs support, you can generate support here also. So you have to go for modify. Here points are there, so you can manually give points like this, and you can generate the support. If you feel the existing support will not work properly, so you can give your support as well. So these are the point support. These can be removed later on. So like this you can add support. So you can see I'm filling the gap by putting points on the middle. So it depends on the part. So okay, I'm okay with the support area. So let's say update supports. Now you will see the density of the support has been increased, and you can do the small changes here. You can change the pattern of this support structure. You can make it pointy as well. So for that, actually as I said at the beginning, when you are selecting the printer, so if you want some there is a printer here called figure 4, this one. In this printer, what you can do, this is specially made for jewelry applications. So if you want to print some jewelry component in DLP Fab Pro 1000, but the proper slicing options are not there for DLP Fab Pro 1000, in that case you can select the printer as figure 4 jewelry, and you can do the slicing here, and then after that you can take that file and you can open that file in Fab Pro 1000, and then you can give the print. So like that also we can do. So for now for this component, this much of supports are okay. These are no issues with this supports, so we can go ahead with this. So what we will do, let's say okay, now the similar kind of support we have to generate for all these files. So right now we don't want this much of file. I just show these things so that how can we use those options. I want only one file, so let's delete these things. I want only one file, so let's say auto place. Yeah, now we are going to print this file. So before printing, we want to know what how much time it's taking and how much material it's consuming. So for that, to know those things, we have to go for the estimations. Here estimate option is there. When you click here, it will show you the estimation. It takes 45 minutes to print and it consumes 8.678 grams of material of photo gray, and it is recommending you to fill the tray up to minimum level. As I said, while showing the tray, there are three stages, three levels. So it's saying you can fill the material up to minimum level, means first up to first level we have to fill the material. So now we are okay with this file. Let's say we are going to print this file. So here one option is there called print to file. So you can click here. So it will show you to save this file in some name. In the format will be .pxl format. So you have to give some name to this. I'm saving this as teeth FDM, and I'm saving here in desktop. Let's say save. Once the file has been saved, you can minimize this. So where I have saved, this is the file. So we have to export this file through pen drive to the machine. So let's say copy. So paste. So this is how we have to prepare the resin before printing. We have to keep the resin bottle in this mixer for 500 cycles. So we have given this rotation, so almost it is done. So we will now we can use this resin to the printer. So I have loaded that sliced file through this pen drive to the system, and we have to operate from here, from this panel. Before starting the print, let's check have we missed anything or everything is properly locked or not. So the tray is okay. This is the tray what I was talking about, and you can see it is transparent. The projector is below, that is going to project the 2D cross section to here, and this bed is going to come down here to the surface, and here we have to fill the resin up to this minimum level. So now everything is fine inside. So now let's follow the procedures. So it's asking now, this is the file what we have saved. Hold button to continue. This button is there, it's showing hold it to continue the print. So when we holding it, it's saying loading the job. Job is ready. Hold button to start. So it's verifying the build. Please scan the material cartridge. So now we have to scan the material. Actually, whenever we have to print something, it will ask us every time to scan the barcode, which is QR code, which is present in this resin bottle, like this. You can see the QR code here. So this is a different material. This is jewel cast green. If we scan this QR code, it won't take that. So for this, we have to only scan that proto gray, in which material we have assigned to the part. We have to scan that barcode. So here our rotation has been completed. So we are going to scan this QR code here. So we are scanning here. Okay. Hold button to Continue. Okay. Now it's asking add material to level, hold button to start. So now we have to add the material in this vat. So as per the recommendation from the software, we have to fill it up to the first level, that is the minimum level. So now we have resin separately in another bottle that we will pour into this vat. That I'll show you how to pour it. So before that, be careful with this resin. So always wear a gloves and mask before doing this thing. So the resin is already here inside in this bottle. It is proto gray. So we have already used this resin. That's why we have kept it in a separate bottle, or else it will be like this in this original bottle. So now we are going to put the resin up to the minimum level, like this. The minimum level has been completed. So I'm stop pouring here. So now we are ready with the resin. Once you added the resin, what it's showing, add material to level, hold button to start. We'll close the door, we'll hold this button, and the printing will start now. It is showing how much time remaining, 44 minutes remaining to complete the print. So now the print will start. We can see the print, but since it is submerged in resin, we cannot completely see what is going on inside, but we can see the movement. So let's say I'm opening this door. So this plate is going down now, so that will be in touch with the film. So there will be some gap between the resin and between the film and the build plate surface. So in that gap, resin will be there. When the projector project the 2D cross section to that area, that will get cured. So now the 76% of the job has been completed, and the remaining build time is 9 minutes. So we can see now here, with opening the door, this is the bed which is moving up and down. You can see if you observe, and you can see the UV light here. This is the current layer scanning. The projector will project that 2D image, and it's getting cured. So basically what happens inside in this resin, this resin is also called as photoreactive resins. That means in this resin there will be chemical monomers and chemical oligomers. So when it gets in contact with the UV laser or UV light, so the light, the exposing to light, it will cross-link together all the monomers and oligomers and create the polymer. So like this way, this polymer creates and it solidifies. That is called curing. Basically, we can see the 2D cross section here in this gap. This is the UV light. So let's wait for another 8 minutes and let's see how the part comes out. So you can see from the screen 99% of the work has been done. We can see what is going to happen now. So you can see slowly the bed is lifting along with the part. Part has been completed now. So we can see there is some additional component with the part that is cured, but that we don't want. Let's see what is that. Let the bed set for 5 minutes, so that all the remaining droplets of the resin will fall down, and after 5 minutes let's remove the bed and check whether we have got our part or not. So as we can see, the remaining droplets from the part has been fallen down. So now we can remove the part. So in order to remove the part, we have to remove the complete bed right now. So it has been locked. Unlock this bed.
and after unlocking we can remove it like this, lift it up and slide it here like this. So this is the bed on which our part has been built upside down. Let's place this part here. Okay, this is our required part. It has been completed. Just there is a small extra cured portion is there that we can remove. Let's do the post processing. To do that, we should have proper gloves like this, and we should have some extra tissue papers and isopropylene, and we need this kind of tool. It is provided by the manufacturer to remove the part from the bed. So if we use some kind of metal kind of thing, then it may cause some lines like this. Some scratches may come in the part and it may damage the part, and it may create scratches on this build plate. So to avoid that, we can use this plastic one. So we have to slice it like this slowly, and we will remove the part. And after removing it, we have to clean it with IPA solution, and by using these tissue papers we have to clean everything, each and everything. So this is the bed on which we are having the part. So we have to remove this. Before removing this, we have to clean the remaining resins on this bed. So let's remove this first carefully. Do not hit to the part. Okay, we have removed as much as possible from the outer side. Let's pour some IPA on this. So now we have this small plastic blade kind of thing. So instead of metallic one, we are using this so that it will not make any scratches on the bed. So let's slide this like this. So it's got solidified. Now we have to use that metallic one. So I'll bring that. Since the part is having very good more thickness, so this plastic is unable to slice that. So we will use this metallic one, but we have to be very careful with this because it may cause some scratches on this bed plate, or else it may damage the part. So be careful with this while doing. And gently we can break the support structure, but we cannot break the part. So we'll do it very gently. Once we get a lift, then we can use the plastic one. Now we can use this. Insert it gently. Okay, little more lift is needed. Okay, finally we got this. So this is the part what we got here. Get a hardened, so we have to cut it properly. We should
By removing the support material to the parts, then you will be curing it in the.
We are getting the solid part, but
Now you put in this curing device
in which
for drying
we
of
are
the
having
part.
a small bed. On
Full
this
of
bed we will keep our
curing
part,
device.
and inside this box there will be several UV lights. We'll see you
UV
after
light
the
will be there.
thing is out, and we will show it to you how it came. So we'll see you after the part has been cured. curing time has been reached now. So teeth and jaw,
This is the
everything
final
is
part that you
looking perfect.
Now let us see the SLA. Right. So this is regarding the SLA DLP. Now any questions from the audience you have, you can ask on SLA DLP. Am I audible?
Yes, sir.
Hello?
Yes, sir. Yes, sir. You are audible, sir.
Any questions from the audience on SLA DLP, you can ask. Yeah, if there are no questions, I am going forward. This is the Ultimaker S5 Pro FDM machine. You have three, this is the world's famous FDM machine you have here. It is from Netherlands. You have three parts here: input metal, from where your spool of wire will be supplied, handling chamber. This is actual where your part gets built up. This is the build platform. And here you have the display monitor, where you can also, here you can put your pen drive, what are the STL file you can feed from here. And then this is the dual extruder nozzles you have here, one for printing the main part, other one is for support structure. You can see the two wires coming here. So based on your material you want to put. So here you can put 1, 2, 3, 4, 5, 6 different types of spool of wire you can put here. The wire goes from here, and at the top you have air manager chamber, where water, the moisture, anything with that wire, etc., will be absorbed by this, will be dried up, so that you will get a perfect print. This is the specification of the FDM printed, dual extrusion printed with a unique auto nozzle lifting system, swappable print course. Build volume is 330 by 240 by 300 mm. The nozzle diameter is core you call 0.4 mm, 0.25 mm, 0.6 mm, 0.8 mm. They are all, we are having all those four. Then heated glass build plate, dual gate abrasion resistant feeder type, and the spool base are 6 with NFC recognition. Incompatible spools with etc. All of them, filter technology, all of them are some of the specifications. These are the various Ultimaker original filaments. Here you can use other filaments also. But if you want to use only company filament, then you have, these are the different grades like ABS, CPA, nylon packs, PLA, touch PLA, polycarbonate, PPX, PVA, PVA, TPO, breakable metals, cleaning filaments, etc. You have here. Let us see this video on how you use Ultimaker S5 Fab S5. Good morning to all of you. Welcome to the last section, that is section number 13 on demo on FDM, SLA and 3D scanner. So I welcome you all to this demo session. Let us see here, we have in this Center for Product Design Development and Manufacturing. This is the Ultimaker S5 Pro FDM machine, which works on fused deposition modeling. As you can see, some job is presently going on, and this machine works on extrusion technology, as already discussed in earlier lectures. So where you take a wire which feeds to a nozzle, which heated nozzle, through which the wire comes down, and the nozzle moves in the XY direction, whereas this is the build platform which will be moving in the Z direction. So in that way the part gets built up. So you can see these are the main these are the main components of this Ultimaker S5 Pro, where you are going to see here the wire feeding mechanism here you have. So presently in this S5 Pro we are loaded with around 5 type of materials. So basically they are PLA, tough PLA, and ABS material is there, and also TPU also is there. And these materials, these wires, you can see that presently this wire is being drawn by the nozzle to the top, where you actually build component is there, where the entire process, the part will be built here. So here you can see this is the build platform, and this is a dual extrusion nozzle you are having. So you can load 2 wires at a time, 1 wire for the supporting material, 1 wire for the printing the part. And this is the air manager chamber here. So in air manager chamber you are going to remove any moisture content, also to maintain the proper temperature inside this. So this works on a software called Cura software. So before you actually build the part, you will be doing the whatever you model in CAD, that you convert into STL file, then you import into the Cura software, where you will be setting up the parameters like the layer thickness, and also with the infill, how much infill you are going to give, what is the raft, and all those parameters you will be putting. And once you set those parameters, then you will be sending that one to the G code will be generated. Based on that, the information will be sent to the Ultimaker S5 Pro, where you will be building the part here. So the entire detailed description how you are going to do the in Cura software, the building the thing and modeling it, and how you set up the parameters, and how you will be sending it to the machine, and what are the steps involved, basic steps involved, starting from pre-processing to post-processing in the FDM process, will be told in detail by our technician Mr. Pramod. In the coming video, they will be showing that the entire process, how this is being built up in the Ultimaker S5 Pro. And these are the specifications you can see for the machine. This is a build volume is 330 by 240 mm by 300 mm, and the nozzle is a dual extrusion nozzle. You have a layer thickness of from 0.25 mm to 0.8 mm, and these are the various materials which you can print here: ABS, PLA, tough PLA, polycarbonate, TPU 95A, PVA for support structures, etc. You can use this for various applications, like you can make for building the model for biomedical applications, and also for proofing your actual product. You can also do for tooling and jigs and fixtures, and all this application you can use it. And whatever the file you develop in the CAD model, that once you convert into STL file, you will input it with this pen drive into this system, and from there you are going to build the part here. Here you can see, at present you can see how much time it is there to build the part. That is presently the part is latest basket is being printed, and there it is saying some total time taken to print this entire part here. And you can also see various, before you upload into the machine, you can see various options here also. You can see the temperature, everything. This will be told in detail in the coming video, right?
Hi everyone, this is Pramod, and in this session I am going to explain you about Cura, which is basically a slicing software. So this software is designed and developed by Ultimaker company, and it is a free source software. Just browse Ultimaker website. From there you can easily download the software for free. Cura software is developed mainly to support FDM technology, which is fused deposition modeling or wire-based technology. So there are so many features that we can change using this software. So this software is made such that beginner can understand easily and work on it. So let me show you the overview of the software. So let me show you the icon of the software. So you can see this icon of this software, Cura. So let me open this for you, but it takes a lot of time to open. So I have already opened it to make it easy. So here is the Ultimaker Cura software. You can find different types of tabs here. I will explain you meanwhile. And let me show you the overview of the bed. So this is a virtual bed which has the same dimensions of that machine. So basically the volume of this bed is 330 mm by 240 mm by 300 mm respectively in XYZ directions, so mm cube. Next thing is that you can go to any view of the virtual bed at any point of time very easily. Here you can see the icons of that. Next, about the tabs. So first, this tab is a file manager where you can load the files and keep the part on the bed. Next thing is that you can see that this tab. So this is so I have already said you that there are so many features. This is one of the feature that you can change the printer settings. You can add your own printer that you have inbuilt, that is inbuilt by you. So you can add your printers, you can manage the printer settings, like you can give the different dimensions of the bed, you can give the different dimensions for the print course, and different material settings you can give in that printer manager. So next thing is that you can see this tab. This tab is basically for changing the material. So if you want to change the material, if you have a own material, you can change. Even that you can customize that. Even in printers, you can customize the printers. Even in software, I mean, even in material manager, you can customize your own material. So let me show you some of the materials like generic. Generic is the third party material. So like ABS. So you have Ultimaker and generic. So Ultimaker is an inbuilt materials that are made by Ultimaker company. Generic is from third party, some other companies. So you can get the outside materials also. Ultimaker, they have provided their own densities, their own melting points and everything. So they made their own filaments. Next, you can manage your materials also. This is where you can give your own material properties, so everything, and you can go for your own material. Now talking about the print course, you can use different types of print cores, like they differ by their nozzle dias actually. So now you can see it's AA.25, AA.4, AA.8, BB.4. You can see different types of print cores here. So basically AA.25, which readily means that the nozzle dia, the extrusion, whatever the wire comes out of that, the extrusion dia of that nozzle is 0.25, and 0.4 means the dia of that nozzle is 0.4. So you can see different types of print cores here. Basically AA and CC cores have different melting points. They range up to 250 to 300 degrees, and BB.4 is basically for support material. The temperature, the melting point of that print core is 200 only. So as to print with the different materials, so we will go for different types of print cores. Next about the parameters changing. You can find so many of the parameters that can be changed in this Cura software. Not just this one, so many other parameters you can find here. So you can, if you go for the quality, there are so many options that are hidden. So you can unhide them by clicking on it. So you can see that it came top, bottom, line width. So this kind of hidden properties also you can change in this Cura software. Before going to explain you about changing different types of parameters here, let me upload the file. So I'm taking a dental part which is all have printed in DLP also, with the size reduction of 50%. So I'm going to do the same with the Cura. So now let me explain you how to change these things. So different types of things here on the left side corner, it's a move option. So you can place your part anywhere in the bed. So next option is that to scale. So as I said earlier, it's been changing to 50%. So now I'm going for the uniform scaling in all the directions. So in all the directions it will be reduced by 50%. So next thing is that it's showing a rotate option. So you can rotate in any direction. It may be in X direction or Y direction or Z direction. So you can change your orientation as you like. So if you want to change, it's a select face to align, it's showing. So you can select the face so that it will be aligned on that side. So you can see I have clicked that side, so it aligned in that way. So I want to place it horizontal, so I'm clicking on the base of that part. So next is that mirror. You can mirror the part, and you can go for multiple parts at a time of the same part. So next option is that per model settings. These are for if you want a fine mesh, if you want the coarse mesh, if you want the fine mesh, you can go for different types of meshes here. Normal mode, printed support. So if you want more number of supports, go for that mesh kind of mesh. So different types of Yes, and if you want to increase your support, if you want to decrease your support, so if you want to apply the manual supports also, here is the option called support blocker. So if you want to give the supports manually, you can go for this. Talking about the changing of parameters, you can see different types of parameters that we can change in this Cura software. First, talking about the profile. Profile is nothing but what kind of profile do you want. If you want it to be extra smooth, if you want to be the print to be rough, you can go for any kind of prints. Like if you go for the fast, the print will be completed at a rapid rate. If you want to go for the extra fine, the time will be increased. So for that you can go for 0.6 mm or 0.06 mm also. If you want it to be completed as soon as possible, then you can go for the fast option. So here there are other options that we can change here. So kind of layer height you can change here also. The maximum dia of that nozzle is 0.4. so if the print core is 0.8, you can go for 0.8 also, 0.4 or 0.8 as you wish, depending on the part quality. So next, talking about the line width, whatever the wire that is extruded, that the dia should be 0.3 mm. If you want to change it, you can change it. So now talking about the wall thickness. So at what thickness you want to print the wall. So wall thickness should be a multiplier of the nozzle dia. Let us say if the nozzle dia is 0.4, so properties of the part, like here try, you can go for 50 degrees also. Next thing is that support extruder. For some materials, the parent material has to be a support
This
extruder.
Ultimaker Cura
But for
software,
PLA,
you can
go
also
for
download freely. It's available online and you can practice a lot. You can take some STL file and put layer thickness, change everything, how the build time, material is changing, and also you can also investigate by changing the hatch pattern or by changing the layer thickness or build orientation. All these things you can study without having a 3D printer. You can study with Ultimate. So it takes the time, but just let me show you how the build part gets built up. Simulation. Oh, you can see this will see.
we can, if you want. So here you can see black refers to, and I will show you about the easy swappable print. So let's go to the show you the overview of the Ultimaker S5 Pro and what are the things that we have to take care before going for volume of 330 by 240 by 300 mm cube. So here we can achieve up to the height of 300 mm. The parts can be printed. So let's talk about the material manager. So we have easy swappable print cores in the build chamber also. Like you can easily swap these print cores and you can change the print core. Let us say now we have AA 0.4 and BB 0.4. You can easily swap that core and you can put the CC core. So let's come to material manager. So it has a dual extrusion technology, range at build and support material in different nozzle diameters like 0.4 mm, 0.25, 0.6 and 0.8 mm. So wide range of thermoplastics filaments were used like PLA, nylon, polypropylene, polycarbonate, TPU 95A, ABS material, and there is a support material which is soluble in water, that is PVA natural. We are also using that. So optimized touchscreen we are having here. So we have Wi-Fi connectivity also. Camera monitor via Ultimaker app. So we can monitor the print while the print is going on. So improved feeder system it's having. So now currently this pipe is for AA 0.4 core for the main material, but you can see there is no material inside this flow line. So we have to give the material, we have to assign the material. Here you can see in the material manager, it is ABS gray. So now it's in the feeder 1. So it's directly go to the AA 0.4 core. So we can manually load the filament. Otherwise we can directly start the print. Meanwhile it will take the filament inside. So we have already we loaded the sliced file in the pen drive. So you can see the port here. You can put the pen drive here so that it can read the pen drive. So you can see now it is highlighted select from USB. So now I am selecting the part here. So it's the teeth UM55 file. It's in the .ufp file. So now I am starting. So it's showing 36 minutes 10 seconds, ABS gray 0.4141 meters. So now just let's start the print. We will see. Meanwhile I will let you know. It's showing that this file is made with an older version, even though it will print. So I am ignoring it. So the print has been started now. Meanwhile I will let you know some other things. So it's now extruding the previous material. Whatever it is loaded before, that is going to be extruded here. Afterwards the ABS gray will be passed through the flow lines. So you can see there the material is. So now the material is getting I am placing it down. So you can see the part. So the part has been completed, and thank you for your patience listening.
So this is regarding the our 3D scanner is a device that converts physical object digital models using projected light patterns in a camera system, which enables you to quickly and accurately capture your object shape, color, and geometries. So 3D scanner, digitizing the object, rapid prototype, reverse engineering, 3D inspection you can use, like a photo, you can build all of them. This is how it works. Light source, projector light patterns, you can see the object. These are basically what you call non-contact type reverse engineering system you have here. It uses laser triangulation method for capturing the object. So we have different models, but we have with a space spider. Scanning, then cleaning that editor tool, then alignment you have to do, then registration and fusion, post-processing you have to do. Artec 3D scanner we have. These are the specification of the scanner we have with us. 3D resolution is up to 0.1 mm, 3D point is 0.05, etc. And the output file is STL or OBJ file. Colored objects you go for OBJ file. Then 3D printing, reverse engineering, 3D inspection, digitizing, around all these things. Using you can scan like this, you can scan the parts. Now welcome to this 3D scanner process. Here you can see. Basically, I hope most of you know 3D scanner is used for reverse engineering purpose, where already an existing object is there. You want to scan it and build a CAD model instead of doing it from scratch, so that you will be saving a lot of time. So this is this whatever we have in our center is an Artec 3D scanner, which basically it works on what you call the Blu-ray technology. Yeah? So you can see the basic components of this Artec 3D scanner is the model which we have is Artec Space Spider handheld. It is. So this is that handheld. So basically the specifications of this Artec 3D scanner is you have it works on laser triangulation method, and it can scanning speed is around 7.5 frames per second. Accuracy you will get
scanner under RUSA 2.0, and basically I'm going to cover up the following things today, like starting like this along with the part, so that you need not to move your hand like this or around the part. You will be in a constant position, and this part will rotate so that you can have
the software is Artec Studio.
with the minimum effort. There are two connections from this scanner handle of that part. So for that kind of part, what we have to do, for certain parts which is very difficult to scan, and we can take two scans in two different orientations, then after that we can align them. So like this, we have to take certain, we have to show the part and the bed as well. So in order to start the rotation, see, now it started detecting the part and the turntable is started rotating. So
Is the table on which you are going to put the object,
start from the bottom,
and this rotates, you are going to scan.
now
Yeah,
you
before
can see
that you have to
the
do
bar on the
clean the
other
surface
side of
and
the
put some
screen,
kind of powder at
and you can
important
see
points.
some numbers are written, like it's
Point
starting
cloud
from
technique.
170 and ending at 330. That is basically the range of the distance between the scanner and the part. Or some extra unnecessary unwanted items also will be covered during the scan. So we have to remove those things during the
Distance between from here to around 0.2 to
and
0.3
the
meters.
important thing was it rotates. We can only barely cover this area. After that, it will come like this. So now what we have to do, we have to clean all the noises here, what you are seeing here, and this unnecessary areas, and this bottom surface that we have to remove. So after cleaning all the noises in all, show you now. Now let's exit from here. Now we can see this is the top area. So we will go. Okay, so this is the scan. So in this we are having this base. So we have to remove this base. For that we have to go to editor. In editor we are having side one. This is the scan, like this edge, and uncheck this one also. Now we'll go to the alignment again, and here we will do by pressing shift, we can move that unregistered one.
There is no cleaning the
not registered
necessary
it,
areas
so it came it like this.
which are obtained when we scan.
Go to alignment again. Here we have to do register both of them. This one also we have to mark as registered. Only the third scan is not registered. Now press shift, drag it, it will come down. Now align this also. Okay, we have to select certain points. So let's see from okay. So now let's move with a more accurate, and so this surface was missing initially in this scan, but it has covered it automatically what it was previously. Okay, so let's compare our model with this. This is the physical model that we have scanned, and this is the model, this is the scan data. See,
Now you can do modeling using this. So, right, sir, you have any question answers? You are welcome to ask. Thank you for your patient listening. Any questions from the audience? I am ready to take.
Thank you very much, sir. The session
I think
is
you would
really
have come
yeah.
physically, that would have been more
Yes,
interactive, but online, okay. As far as possible, we have shown what is best possible thing.
yes, sir.
Yeah, any audience you have questions, you can ask.
Yes. Participants, you have any questions, you can ask Shivaramakrishna, sir. Sir is given time to us. Okay, because sir is very busy with Usmania University works. Okay, if you have any doubts or any clarifications, if you want to implement this type of facility at your own institution, also you can ask, sir. Okay, sir will definitely guide you.
Yeah, definitely like this, we'll arrange a demo sessions to you. Actually, like this, we have done during COVID time. So most of the FDP programs online were only theory classes, but we have conducted online demo of the actual practical sessions during the COVID time.
Yes, sir. That's right.
So anyone interested to conduct a programs like what Anurag University has done, they can also come forward. We'll plan something suitable to your requirement. Tomorrow, I think you are going to have a demo on SLM, SLS, and Polyjet by Professor Sriram Venkatesh.
Yes, sir.
Is it right, sir? Tomorrow morning?
Yes, tomorrow morning, sir. Polyjet. Yes.
Polyjet, SLS, and SL.
Yes, correct, sir. Yeah.
Any questions from audience?
Yes. They are saying that there is a best session, sir. This is an excellent one, sir. And they are saying in messages.
Thank you.
Yeah. I think, sir, for this program, we have gone through all technicalities, sir. Because morning also one session is industry session, morning.
Okay.
So
Yeah.
they have given insights of what industry is expecting from the mechanical engineering
Okay.
department.
On 3D printing side.
Yes, on 3D printing side only. And what the industry is expecting, the students, okay, from 3D printing. So they are also said that every institution will have 3D printing facility, and the student must know that knowledge.
Yeah.
Then there is a plenty of jobs
Yeah, correct.
in the 3D printing sector. So I
Yeah.
think this is most of the participants are faculty only, sir, in different universities and different institutions.
Throughout India. So I
Yeah,
am
throughout
seeing
India. Yeah.
70 participants are there this side.
Yes, now 70 participants are there, sir.
There's a good strength.
Yes, sir. And we are sharing the PPTs also, sir. And this
I
today's
will
PPT.
share,
Sir.
this, I think these videos, etc. I'll share the Google Drive also. But last week's, last time my
Yes.
presentation, I'll share the PPT.
You can share the
By
PPT
tomorrow-
today, sir. Actually,
By
participants
evening,
are asking.
today or tomorrow morning, sir. Today we are having graduation day. Now I'm going there.
Yes. You are busy. Yes.
After
sir.
today night, we'll be here.
Yes, sir. Okay, sir.
Thank you.
By today,
Nice.
you can. So tomorrow you can share.
Tomorrow
sir.
morning, I'll send. Yes.
Thank you once again, sir.
I'm
Thank you
having
very
a
much for
lab
your-
examination, so continuously from morning 7:30 to night. So I am going to be late.
I
That's
think,
why I
sir,
could not
tomorrow.
share.
Yes, sir. Actually, tomorrow we are conducting afternoon session is a assessment test, sir. So
Okay.
those assessment test questions are coming from the sessions only, sir. So that is the
Okay,
problem.
definitely I will share, sir.
Yes, sir. Sriram Venkatesh sir also said, sir, the PPT.
Okay, I'll share.
Yes, sir.
Thank you,
Sir. Thank you very much, sir, for your. I think there
I
is
am
no
leaving,
question
sir.
from the participants. Yeah.
Okay.
I will tell you. Thank you, sir. Thank you very much.
Thank you, sir.
Requesting participants, please fill the feedback form. Okay, I have shared to everyone. So I think Shravan sir, are you there?
Yes, sir. Yes, sir.
Yes. I think your name is not getting in the chat box, sir. In which name, sir, you are logged in?
Shravan Kumar, sir.
Okay, 1 minute. I am checking.